Hi, or should I say hello? In fact, the µSupply says hello. Yes, I know it's been an incredibly long time. I still get constant emails and messages from people saying, hey, whatever happened to the µSupply? Are you ever going to finish it, ever going to get back to it? Well, here is part whatever. Actually, I don't really know what part of this. I think there's 15 official videos, but there's actually more than that because I did 2 videos on designing this custom LCD here. I'll link them all in. I'm pretty sure I done videos on like custom heat sinking and stuff like that, custom keyboard, keypad design. Anyway, I thought that I'd go back to it and revisit and show you where the µSupply actually got to. And yes, here it is. Here, it is an actual functioning product, and I do use it occasionally. It is quite funky. Look at this. It's got basically customized everything. It's got a customized case. It's got customized keypad, customized LCD, which I've done a video on, customized planar transformer in here, which I don't think I've done a video on. It's got customized heatsink, customized connectors as well. Believe it or not, I can do a teardown and show you this, but anyway, this is not necessarily an official restarting of the µSupply designs or a continuation, but I show you where I got to and what its current status is. Right off the bat, no, you cannot buy this, okay? There were only a few of these prototypes made, and they do actually work. So you can actually see here. Here it is here. Boop. There it is. It's actually hooked up to a load and it's drawing 200 milliamps here. And you can see the set voltage and set current are up the top here. And then you've got the actual measured output voltage and the measured output current here. It's got a nice big customized hello here, but that can be used for all sorts of stuff. And it's a pretty funky little thing. You can actually, if we want to program the current up here, for example, if we wanted to only go to say 100 milliamps like that, we could enter 100 milliamps and boom, it drops down to 100 milliamps. It entered constant current mode down there. And yeah, it's a nice little supply. It does actually work. It's got USB-C input over here like this, so we can power that on and boop. There it is, and we can jump right back in there, and it automatically stored the milliamps up there. And one point, it did actually have a Skippy command interface working at one point, I think, but I don't think this particular one actually it is programmed with that at the moment. But anyway, it does look very cool. And basically, the story behind this is that, of course, David too, when he was working for me, he was the one working on this project at the time, and then when he left, we did like a handover of all the documentation and all the all the design files and everything. Still got a folder with all the stuff. I've got a giant tub with all the parts and everything, all the miscellaneous parts and prototypes. And the thing was, I just kind of like lost interest in it and went on with other things. Like, as cool as this product is, I think it's very cool. I do think it's actually too limited and somewhat a product of its day. I would actually design it very differently today, and I'll actually take you through a quick go through of the design files of this thing, but I'll show you inside. Ta-da! This one, actually, there's one of the, there's your problem. Well, no, it's not actually a problem. There's one of the things, right, believe it or not, that everything is custom in this. Like, that connector there, banana plug interface, is a custom interface like this. It wasn't soldered, this one wasn't soldered in there for some reason like that. But basically, yeah, we got the banana plugs custom manufactured like this. We got the heatsink custom manufactured. This planar transformer here, that's a custom manufacture. There's a top-down look at it there. It's got dual processors. There's a secondary side one, and there's also a primary side processor as well. And you can see on the bottom, there's no components. It all was a top side load here, and the case had metal threaded inserts in it. Check that out, Bobby Dazzler. And it was just basically the big custom LCD on the bottom side there. And this is under the heatsink here. We've got two power transistors under here, and that was just the bottom side of the heatsink like that, which, you know, was quite a nice little fit to envelope design like that, just to go over the top. And of course the bottom had these holes spread over like that, so the airflow would actually run through and over the fins properly. This was pretty much was supposed to be the finished µSupply. Although I don't recall absolute details. Sorry, I haven't gone back through and extensively looked at the documentation and stuff like that. I just switched on the camera, thought I'd give you an update here. But I do believe the final conclusion from David was that we probably should go away from the Planar Transformer. It wasn't as good as we thought it would be. And actually, I can show you an old prototype. We didn't always go with this custom Planar Transformer. Here, oh, I just noticed the date code. Is that really the 24th week, 2019? Wow. Here's an older prototype, for example, and we used some off-the-shelf isolated converters, because that's one of the things with the µSupply is that I wanted it to be fully isolated. And with hindsight, that was probably not the best idea. It was quite nice, you know, to eliminate any ground issues. But in practice, most people are going to use this with an external battery pack or something, you know, a power bank, or they're going to hook it up to their laptop, which isn't, you know, which is floating anyway, as long as you don't plug in the mains connection. I've done a, you know, whole thing on how to not blow up your oscilloscope, how to not blow up your computer and stuff like that. So really, you do pay a huge penalty for having the isolation. If I was to do this, if I was to release an actual product, I would just do away with the isolation. And also we paid a price because you've got to have secondary side process, isolated side processing. Not only do you have to do the USB power delivery negotiation, which by the way is much easier these days. There are much easier solutions to do USB power delivery. Back then, it was harder. And you can check out the source code, by the way. It's been available on the GitHubs for ever since David left, I think. I actually released the software for this. So yeah, we just ended up with multiple processors and a really complicated USB power delivery solution, I believe. And it just wasn't God, you know, you wouldn't believe the amount of effort that just went into getting the USB power delivery working, for example, and then having processor isolation and, you know, primary and secondary and stuff like that, and getting the serial over, and, you know, it's just messy. I would have, if I was to release a public product, if I was to sell it, I would just ditch the isolation. I don't know if you think it's important. Please leave it in the comments down below. But at this stage, I have no intention of actually going ahead and finishing this to an actual saleable product. But you never say never. Anyway, so you can see this is our prototype 1.0. So yeah, it's got a couple of bodges. I'm not sure what this battery bodge here is. I don't know. He was maybe experimenting with, you know, putting a DC bias in some part of the circuit or something. So that was basically version 1. And you can see that we had a different solution for the banana jacks down here. For example, we had this little, you know, right-angled board with the pin headers, and just used off-the-shelf stuff like that. And at some point we decided it was better to actually design this custom thing, because you can actually get little folded bits of metal like this, actually custom manufactured real cheap. It's not much NRE on it, and it's, you know, the unit cost is, you know, not much at all in the scheme of things. But, you know, everything adds up. Just having everything custom on this, it really adds up. Although, you know, as you see, it's a real sexy final product. If you want a real sexy final product, you know, you've got to do custom stuff. So I think most of the electronics is the same. You can see it looks very similar, the power section over here. I can't actually remember details. I haven't actually looked at the schematic. We'll go later and have a look, so you'll be seeing it fresh, as will I, after many years. But yeah, we decided to, because these were quite expensive, the off-the-shelf isolated converters like this, so we went for double to get twice the power output, if memory serves me correctly. So we thought we'd try this custom planar transformer down here, and I don't think it worked out as well as we expected. It worked, but it just didn't give the power envelope actually required. So yeah, if I was to design this again, I'd just ditch all the isolation and then just have one processor instead of multiple processors. I'd change the USB power delivery thing wherever that is, and yeah, because there's much easier solutions for that these days, like single chip solutions that are pre-programmed. You don't have to write any firmware, but just pre-programmed, pin strap it, what power level do you want, and it'll do the power delivery negotiation for you and stuff like that. Whereas we had to do it all from scratch back then in like 2018. Anyway, that's enough waffle on the hardware, but I hope you agree. That is one sexy bit of kit. And one thing I really like is the LCD on this. I mean, it just looks absolutely like fantastic. Like, you know, big digits. It's got the separate programming ones up here. It's got, you know, a customized display down here and nice big enunciators on, and, you know, you can just see them, and it's got other enunciations. You can change, you know, to watt hour display and stuff like that. And David, he absolutely insisted on having joules. So, because he's a joules fanboy, so he absolutely insisted on having a joules capability. So it's got that too. I don't know if it's programmed, but yeah. I think it is. And then it's got different modes down here which you can set, and set limits, firmware 1.00 for example, reset, calibration, and beep and reset enable, and, you know, all sorts of functionality like that. It's got a lock function, and it had programming modes as well, but I don't think they were actually programmed in. So, but anyway, yeah, I love the LCD. I always thought about maybe designing, like, or just selling the LCD so that people can use it in its own, in their own projects and stuff like that. Or maybe, you know, design like a little universal board for it so you can retrofit old product. Because the LCD is, it's just, I really like the design of it. And it just looks beautiful. The contrast is excellent. Oh, it's Bobby Dazzler. Thing of beauty. Joy forever. All right, let's take a quick look at the schematic and the PCB to see what we've got here. Now, this is the top level schematic here, and this is just the overall links in other sheets here. So we've got the LDO, we've got the pre-buck, we've got the USB isolation, we've got the main micro part, and the HMI, which is the human machine interface. And like a handy little note here about where the binding post came from. And as I mentioned, they are actually a custom, we got them custom machined, the post machined, plus we designed our own little right angle connectory, PCB connectory, spring connector thing, which I believe doesn't need to be soldered. It can just be a press fit. But, you know, if you're keen, you can solder it for extra reliability. It's like we can go into the micro, for example. And so there's all sorts of stuff. Look, there's options up here, DigiKey. Like, I have not looked at any of this for like over 3 years. Yeah, so this is the main micro, and we use an STM32F072C8T6 for those playing along at home. And yeah, another one of the reasons was production, of course. You couldn't get the STM micros. They were like, a lot of the parts became really hard to get for a long time. I believe that was one of them. So yeah, we've got I can't remember why we chose that particular STM micro. You know, they've got so many variations of it. Anyway, got some regulation here. We've got an E² prom. That's over on its own schematic. There it is there. It's just, that's the only thing on it. This was a thing at Altium. I didn't draw this, by the way. This is David too doing this, but this was a thing at Altium, and it was in all the examples, and then everyone in the industry started to copy it. It was like, okay, you're going to put just the one E² prom on the one sheet, on the one schematic sheet, and then you treat it as a sheet, and then you do the modular thing like at the top level here, and then you put it there. Like, why couldn't you just put the E² prom there? It was part of Altium's modular approach. You wouldn't have to design your own boards anymore. Altium, at one point, I kid you not, made the PCB tool optional extra. Oh. That didn't last long, but the whole idea was that everything in the future would be modular, and it would be, you know, you wouldn't have to lay out your own board because someone has already designed an E² prom. Why would you have to design your own? Just drop it in, and the layout's already done for you. Why would you have to lay out your own board? Just drop it in, and all these modular, and it was all supposed to be, the future of PCB design was supposed to be modular, and of course it never happened. So if you see, there's a lot of people in the industry, yeah, we'll just put one sheet, and Altium's to blame. Wasn't me, even though I worked there. I just don't blame me. Okay. Yeah. So we've got the voltage set DAC and the I set DAC here. So we're using the external, like the DAC output in the STM32 because it's good enough. Like, this is not a hugely precision supply. The internal, I can't remember, it's probably a 12-bit DAC. Specs aren't great, but good enough for Australia. So that goes off to the regulation part. Right, so here's the USB isolation part, and we've got these are all different sheets, so we can go in and have a look. So I'm not sure what it says. Rough simulation up here. Swap for P-channel JFET if this doesn't work. So I'm not sure if this was part of the final one or whether or not he selectively left these out. And this is a flyback option. So I can't remember exactly what's doing there. Anyway, let's go into the USB sheet over here. Once again, there's a few notes down here. USB-C, 5 volts, USB-B-C, 1.2. So yeah, you've got to remember, this is not a production-ready schematic. This is a prototype schematic. If we went into production, it would have been, you know, it would have been tidied up. And you can see how on the isolation side, we used another STM micro here. This is the STM32F070. So this is what we did the USB power delivery stuff in, I believe. And it was a huge stack. It was massive. Because at the time, as I said, there were, I don't think there were any like really easy to use off-the-shelf power delivery chips available. They came like a year or two later. And now I think there's plenty of them on the market, isn't there? Where you can just plug in the chip. As I said, you can strap a pin, and they're designed for use in simple products. But back then, like, there was, I think it was like 32K micro just to hold the stack for doing the software stack, for doing the powered USB power delivery negotiation and everything else. It was provided by ST, but we had to massage it a lot, and we had lots of issues with it and all sorts of things, if memory serves me correctly. And it was, you know, but it worked. But oh geez, no, I wouldn't wish it upon anyone. It was just horrible to get USB power delivery working back in 2018. Actually, we did use the RT1716. Let's have a look at that. Yeah, now it's all coming back. Yeah, we ended up using this Rich Tech job. I think this was in the second revised one. I don't think we originally used this, but this does the hardware negotiation for this. But you know, it's this is a relatively simple chip. Yeah, I think we ditched the older solution. I don't have to pull up the older schematic. We found this easier solution, so we actually redesigned it, I think, using this Rich Tech programmable USB-C PD controller, and it's just had an I2C interface. That's right. So it was just simpler, but we still needed that isolated side microcontroller in there. So it's a much smaller device, but than the main micro that drives the LCD and the keypad and drives all the DAC power supply functionality. But you needed something when you have isolated supply like that. You need something on the isolated side to do the USB power delivery negotiation and stuff, as well as doing the serial comms, because we wanted to send serial back so you can do the skippy commands and the whole works. Yeah, so it looks like we ended up using that. Anyway, like, each aspect of this design could be a 30-minute video in its own right. So sorry if I'm going to skip things. So we just had a simple 3.3 volt regulator there just to power the local micro here. So there's notes down here about use this SI2333 part. If ESR is problematic, this limits the voltage to 9 volts. So anyway, that's the V-bus. There's our USB connector there. So we got our USB comms and the CC1 and CC2 pins, which go over to the controller interface, that Rich Tech controller over there for doing negotiation. And that's just some soft power stuff. Then we've just got a programming interface there, and pretty much that's all she wrote on that side. Although no, we've got the UART isolation here you go. So this is how we got the serial comms over. So we just use this Skyworks here, 8641, a low power quad channel digital isolator. It didn't need to be too quick. You know, it's what's it? Oh no, there you go, high speed, 150 megabits per second. I don't think we needed that high, so Not sure why we used that one. Again, the choices have been, they were documented somewhere. We'll probably have the documentation for it. So basically, we've got our microcontroller here. We've got our USB power delivery here. We've got just the USB input here, programming header, local regulation and isolation, and then bingo, here is our big isolated converter with our specific planar, this would be planar transformer, and we've got a characteristic curve here. And, you know, there's a couple of engineering notes in here. Change to 82K, no difference, for example. So, yeah, you know, David's obviously making notes in here as he was testing the thing. As I said, this is not a production schematic, so yeah. We used an LM3481 switching converter here, and the planar transformer, that was a custom transformer. That number would have been generated by the manufacturer. I can't even remember who manufactured it off the top of my head, but we got it custom manufactured, the planar transformer. We'd probably have the data sheet for that somewhere, I suspect. Oh, look, isn't that neat? I was just browsing through the directory here, and I just found like an early 3D thing. We obviously didn't have the keypad in there at the time, but that was just an early concept. Cool, huh? And there's another one. Check it out. This is before we had settled on the keypad user interface, and we were using off-the-shelf case here. So you can see it like end caps. So that I can't remember who manufactured that case, but you can get like the LCD cut out in there, and it would have had rails in there to slide it in, and like to slide the PCB in, and it says 6 watts up the top here. So we used actually 2 of those 6-watt isolated converters, as you saw in one of those original prototypes there. But yeah, we never physically made this interface, but you know, we just went with the keypad one in the end. Once again, I can't remember why. This one would have been a bit smaller form factor than what we've got. Same LCD. The LCD design was settled like very early on, and we didn't really change that. It was just, you know, there were several different design iterations with user interface type stuff, and we settled on the keypad. Let us know what you prefer. Do you think that we nailed it with the keypad version that we've got now, or would you prefer something a bit simpler like this? I kind of like the keypad one. You know, you could enter the numbers, but I can see the simplicity of the up-down current thing, but we just wanted a bit more versatility, I think. And then once we decided on that, then it pushed us into a custom case, and this is quite common in the design of products like this. It can, you know, especially when your specs are flexible and things like that, you sort of, you know, you make one change, you decide on one thing, and it sort of like pushes you, oh, now we need a custom case. Oh, now I've got the custom case. Oh, we need a custom, you know, we can do a custom heatsink, and oh, we could do this other thing, and we could do this thing, and, you know, oh, we can add a bit more power, so we'll do our, you know, our own isolated planar transformer, and like, you know, it's just, yeah, it goes on and on. You can go down the rabbit hole. Anyway, let us know what you think. And that's just the full LCD, but I've shown that in the LCD design video. I have no idea what that is. I don't know what that is. What the? And then there's design notes and documentation like this. I found some random documents in here. Clearly, we're analyzing the amount of flash memory required for various things, the amount of SRAM, you know, the flash, like we're going through different choices for the different micros there by the looks of it. Yeah, so these were just like selective copy and paste from the data sheet into your own design document. That's a common technique, just to so you don't have to search through. You've got it all, like if you extract the important stuff, copy and paste them out into your own design documents, and then obviously, you know, we're mucking around with this. And then there's other random design analysis stuff, negative rail solutions, for example, availability, like, you know, risk, total cost and things like that, you know, which is the lowest risk solution for generating a negative rail and stuff like that, you know, just little design things. Then just some notes on the efficiency of, or the potential efficiency of various switching regulator chips, for example. And some compensator design notes, for example. If, once again, yeah, I won't go through them all, but yeah, neat. You know, a lot of effort was put into, you know, various selection and design processes of all the stuff that went into this. And there's just a close-up photo of our custom planar transformer there. You can see the multi-layers in there. If you don't know what a planar transformer is, it's basically a PCB, and it's a multi-layer PCB, and they just put the turns on flat on there on the multi-layer PCB, and you get different thicknesses. And copper, I've done a recent video on that. And yeah, you can do, there's some efficiency advantages to planar transformers, but basically a real low profile thing. That's one of the major advantages to the planar technique like this, is you can get all those turns in a little nice smallish form factor. And before we physically built anything, we would do like 3D renders like this, so we could, you know, really get a feel for it, and we could, you know, pan it around and everything, get a real feel for, you know, what it was going to look like. So that looks like, yeah, that's our finished design, is what we got. It looks almost identical to what we got. Anyway, back to our main isolated switch-in converter here. And we've got a classic TL431 down here, and then just a feedback opto isolator here. It's, you know, it's pretty much straight out of the LM3481 datasheet, I think you'll find. And, you know, that's where all, you know, formulas and stuff come from, perhaps. You know, once again, go check out that. Follow along at home if you want. Modified set point, 15.5 volts. All right, so we must have another track-in pre-buck. There it is, pre-buck. I mentioned that at the start, didn't I? So yes, this is the track-in pre-regulator, which it means that you minimize, or you keep a fixed voltage drop across your output pass transistor, so you've got a known power dissipation, which is why we could use a relatively small heatsink in there. To, you know, very low, quite low profile heatsink. Doesn't need much square area at all, because we're only dropping at most, you know, like 2 volts, for example, across the output pass transistors. Then at 1 amp, you're only talking 2 watts, for example, which you could dissipate in that heatsink. It's much easier. And here is the pot. Okay, here is the digital pot here, and that's how we adjust it. And yep, there we go. It's an AD5260. Go and look that up for yourself. You'll find that's a digital pot. Not sure how many steps or whatever. But yeah, that's often one of the easiest ways to do this sort of thing, is to use a digital pot. It's more expensive. Like the digital pots generally aren't that cheap, especially like an analog devices one down there. But it's just a nice analog-y way to do it, because you're still in the analog domain here, and it's just, yeah, it's just easy. Oh yeah, there it is. The net over here is labeled 15 volts. So that switching, that main isolator switching converter, a fixed 15 volt output there. I think we did actually investigate actually using that as the adjustable and getting that adjustable, but it was it was just easier to use a, this is an AP5313. Huh. Not recommended for new design. There you go, the AP3513. So even if we went with that, it's obsoleted already. So 18 volt, 3 amp synchronous buck converter. Yeah, so it's just the application circuit here, and you just replace R1 here with one of those digital pots. Bob's your uncle, you can get your tracking pre-regulator, easy peasy, lemon squeezy. But I guarantee you that part would not have been not recommended for new designs, which is effectively obsolete. Don't use it. Unless you like got an older product and then do a last buy or something like that. Buy all you can, because we're not going to make this sucker anymore. Yeah, so that would not have been the case when we designed this. That was only less than 5 years ago. So yeah, it's gone ski. So here's what you're all here to see, I suspect, is this LDO. What do we got here? Yeah, we've got a whole bunch of design notes, I out, V-Sense, okay. So we've got 2 output pass transistors here. They are the same, NTD2955. Couldn't tell you why we selected that. It might be one in one of the design note documents here. We've got a 1 ohm current shunt resistor here, then just a differential amplifier. I think in the previous version, we tried to get away with something much simpler than an OPA for, like, we'll say, trying to save like every cent on the cost. And I can't, yeah, anyway, we went with just like a regular op amp here. This is not a differential, like a proper current shunt, like high side current shunt op amp. It's just an op amp. Yeah, it's nothing special about that at all. It's just a 10 meg rail to rail automotive grade op amp. So yeah, no, we decided, I guess for cost reasons, not to go with a like a proper, like a high side differential, because this is a high side, it's not in the low side. If it was low side, it'd be, where's your ground? Where's our ground pin? Where's our output ground pin? It's not there. There must be on another sheet. But yeah, it'd be on the low side, which on the ground terminal. So that'd be low side current sensing. This would be what you'll call high side current sensing. So if you're after a proper differential amp to do this, then you'd be looking for high side current sense amplifiers. But we just used an op amp there. No worries, does the job. So obviously this here is all part of our current regulation circuit. So we've got current regulation. So this is our current regulation pass transistor, and this is our voltage regulation pass transistor. And if we're not in current limit mode, of course, this is just like basically a short circuit. It goes straight through, and then this transistor here is the one that's limiting your output voltage here. And once again, I could do a whole video on the design of this thing, but I believe that looks like our final, yeah, that looks like our final output stage here. Do we, oh yeah, okay, no, we didn't reuse that. That's a different op amp. That's a OPA 2180. That was an OPA 4172. Oh, there's the 4172 again. So 4172, OPA 2180. So we're using 2180 there, and this one there, and there. I'm not sure what's going on. Oh, and up here as well. So that's a quad jobby by the looks of it. No, the 72 on the end. No, is that just a dual? Whatever. So anyway, you can knock yourself out analyzing that if you like. We've got the formula there for getting the output current there, and it's just a standard configuration for the output voltage drive here. We've got a TVS on the output. We've got a PTC for protection. Not a huge amount, and this is just tapping off. That'd be going over to the microcontroller to, you know, when you saw 12.01 volts on there, that's where it's getting from. It's just tapping it off there. And that's about all she wrote. Oh, and then I forgot down here to know if we're in constant current or constant voltage mode hardware-wise, so the micro could tell if, you know, if we're in constant voltage or constant current. There's a dedicated circuit there, LM321, just a comparator here, and it just knows which one, and then signals the micro there. So yeah, that's just power for the op amps, and so there it is. That's the output circuit. Once again, you can make it simpler than that. Once again, I couldn't tell you the exact design decisions, but this has changed a lot over the years, especially in my hands up. Who wants to see a video? I've got them right here, actually. I've had them sitting out for ages, so I'm probably going to do the video, but leave it in the comments down below because I may not get around to it, so kick me up the backside if you want to see the whole history of every, I think I've got every µSupply prototype I've ever done. There's like half a dozen of them all through the years. This project has been going on before I started the EEVblog. That's how long ago. I can remember when I had the first prototype. I was working at Altium at the time, and Leo Simpson, the then editor of Silicon Chip magazine, he was visiting Altium for some reason. Just dropped in to say hi. I don't know, chew the fat. No idea. Anyway, he knew that I was working there, so he dropped by my cubicle, found out where my cubicle was, dropped by my cubicle, said hi, and I happened to have my original µSupply prototype, because this is before the blog. I was thinking about, you know, publish it in Silicon Chip magazine. I go, hey Leo, check this out, and he loved it. He thought it was an absolutely fantastic idea. It fitted in the Jiffy box, just like the microcurrent, fit in the same Jiffy box as my microcurrent, and it had knobs and a LED and dual LED displays on it, I think it was, and he just loved the idea. And yeah, so but I never got around to finish it. I changed the design a couple of times, and I never got around to publishing it in Silicon Chip magazine. So I don't know, but he thought it was fantastic. He was desperately waiting for me to finish it off and write the article, because he loved the look of and just the idea of a USB µSupply. There it is. Back in 2009, that was 2009, and then it upgraded to 2010. So thumbs up, comment down below if you want to see a video looking through all of the different history of the thing. So yeah, this is just it's just been a fun hobby project of mine, and it almost made it, but anyway, I'll tell you about that at the end. Would you like to see just a quick look at the PCB here? So here's just a 3D version of that, but you're seeing the thing in real life, so it looked pretty, it was pretty spot on, actually. Yeah, that looks pretty good, doesn't it? And it's a 4-layer board, obviously, and you can see the layout here. It's, it's not much to it, really. What can I say? Yeah, we've got a split plane in there, obviously. So there's our component side, internal power supply plane there, just separating them, internal ground plane, so they were physically separate. And just bottom side there, in fact, there's hardly any traces at all on the bottom side. It's all going over to the LCD there. Oh yeah, I forgot to show you the LCD. Human machine interface, is it? Human machine interface. There we go. So there you go. That LCD had 8 commons there, and however 31 segments, and a HT 1622 LCD driver. I think we couldn't find the some ST micros, of course, have built-in LCD drivers, but we couldn't get it, or it increased the cost too much, and it was cheaper to get a separate chip. So I'll look that one up. So that was just a Holtec jobby. Holtec's one of, they make their own micros, of course, and they make LCD drivers, and they're pretty cheap. I don't know exactly the cost of that, but yeah, it supported 32 segments, 1622 with 8 commons. So we practically maxed out that whole thing. So yeah, it was just cheaper and more better just to get a separate LCD controller, because then you weren't really constrained with the ST micro or your microcontroller selection then if you try and get it built in. Sometimes you win with that, but this required a lot of segments, a lot of commons. Like, it was quite a complex LCD on this thing. So yeah, it was probably a no-brainer at the time for us to go to the external LCD controller. So there you have it. I hope you enjoyed that update of the µSupply there. Yeah, as I said, at this stage, I have no intention of actually releasing this as a finalized product. You might get, Dave, the meme, just, shut up and take my money kind of meme. I don't know, leave it down below if you want to shut up and take my money. But I wouldn't go ahead with manufacturing this. I think these days, there are portable power supplies now. Back when I was doing this, nothing existed. There was no such thing as a USB power, like a portable power supply. Now there's a few on the market. I still think this is by far the coolest looking one. But I think with the isolation in there, we could get the bill of materials cost down, because the bill of materials cost was getting quite high on this one. I was getting concerned that it was missing the market segment with the multiplier I had to add on it and everything else. I thought, it was would people pay a real premium for this thing, or is price more important? Once again, leave it in the comments down below. Would you pay anything for this, or would you go, oh no, I'd only pay $50, or I'd only pay $100 or whatever, and by adding a whole bunch of stuff, it all starts adding up. So yeah, if I was going to go ahead with this, as I said, I'd probably just drop the isolation and just have a simpler USB solution chip. Although that one we had was, is fairly decent. You just have to send it some I2C commands, and Bob's your uncle, I think. But as I said, there's even simpler ones now, which I think, like an 8-pin dip or something. Offhand, I couldn't tell you the number. Leave it down below if you know of a good one. Where you just pin strap the thing. They're designed for ultra simple products that are powered from USB, and you just, all it does is negotiate. You strap the pin and say, I want 20 watts or whatever the, whatever USB standard you want. And it just negotiates the highest one up to that, depending on the capability of the supply that you actually plug into the thing. And and then it just simply supplies that. And then I just have there's even easier solutions for tracking pre-regulators these days and stuff like that. Might make it entirely switching. I might go with a simpler output stage than the one the LDO stage that we did here, because this is quite a low noise one, so you might not worry about low noise. You can make it cheaper, and you can have just a switching a complete switching solution really there are solutions out there that, you don't have to muck around as much as we've done here. So, you can really cost optimize those ones. All those cheap power supplies out there these days, they don't go to town like this, right? They're much cheaper, much simpler, and you just who cares if it's got a bit of noise on it, she'll be right. I'd rather have the lower cost and the simplicity. Anyway, let us know your thoughts down below about the µSupply. I hope you enjoyed the update, and if you enjoyed this video and you want me to make more on continue the µSupply series in whatever form, please, or if you want more detailed stuff on something that I've done here, let us know in the comments down below. If you liked it, give it a big thumbs up. Discuss down below, EEVblog forum, you know the drill. Catch you next time.